Um, so as we start our next unit with systems of equations, a good place to start with that is really because we're going to get in the bulk of this is solving systems algebraically, and methods for that are substitution and elimination, which again you've all done at some point. But a good place to start is actually by solving these with graphs and kind of tables. We're going to focus more on the graphs, but a table's another resource to solve them. And the reason that we start this way because every system that we solve, there's going to be a graph that represents the situation. So just some introductory vocab into systems and just things to know is that when you have two or more related unknowns, unknowns being variables, you may be able to represent the relationship with a systems of equations, okay, which is a set of two or more equations. We're only going to be working with linear equations. Okay, we will actually do something with three variables. So I guess that's not technically linear, but the three variable systems get to be a little confusing. And so know that a linear system consists of a linear equations, and the solution to a system is a set of values for the variables that makes the equation true. And then we can solve that by graphing or using tables. So for the most part, our solution, this pen is dead. Our solution to most systems is where the graphs intersect. Or let's say is where the lines intersect. And because it's going to happen at some point, the solution is going to be written as x comma y. Now, if we're working with a word problem, then it may not make sense to write it as an ordered pair or an x comma y. But for the most part, especially today as we graph them, we're just going to simply be looking, where do these lines intersect? And so we're going to actually just start with that. And right now, the two equations that I'm seeing here are not in a form that are easily graphable. Yeah, I could go ahead and find the intercepts. I'm noticing if I do find the intercepts, I'll probably have some fractions, which is okay. But I don't know that's going to help us actually pin down the exact location of where these lines intersect. So what we're going to first do is take each equation here, and we're going to solve them to get y by itself. That way we get it into its slope-intercept form, and then we can easily graph it. So I'm going to add 3x to start. So my equation is now 2y equals 3x plus 8. Then I'm going to divide every single term by 2, making that y equals 3 halves x plus 4. And we can go ahead, we'll save the graphing until we have both equations ready. So my other equation, x plus 2y equals negative 8. Again, I'm trying to get y by itself, so I'm going to subtract x. So 2y equals negative x minus 8. Divide by 2, divide by 2. I get that y equals, when we have negative x over 2, the better way to write that, especially when we have to graph, is going to be negative 1/2 x minus 4. Okay, that way it's just much easier for us to identify the slope. Okay, so maybe let's make a side note that negative x over 2 is the same thing as negative 1/2 x. Okay, so if you see like the x on top, that really means there's a 1 there, and we're multiplying that whole fraction by x. Okay, so we're going to go ahead and plot these lines. So starting with the green, 4 is my y-intercept. I'm going to put a dot on the y-axis at 4. And then my rise over run is 3 over 2. And it should be a positive slope line, so I should see it sloping to where it's going up to the top of the page as we move to the right. So I'm going to go up 1, 2, 3, and right 2. Up 1, 2, 3, right 2. And then after going up and right, I could also do the opposite and go down 3 and left 2, just so that we're getting all of our points, or as many points on this graph as possible. All right, then for the red line, negative 4 is the y-intercept. Put a dot at -4. And then with the slope of -1/2, I should now see my graph or the line sloping to the bottom of the graph as I go to the right. So to do that, I can go down 1 and right 2. I'm not going to do that the whole way through because that's not getting me any closer to finding where these lines intersect. So now that I've gone down and right, I'm going to go ahead and just do the opposite now and go up and to the left, as that's going to take me closer to this green line and thus the point of intersection. And that's really as far as we need to go, just as far as possible to find the point of intersection, which these graphs intersect at -4, -2. Right, and we can check this if we wanted to make sure this is correct, which we will do at some point. We'll save that for tomorrow. I'd plug in -4 for each x, -2 for each y, and we're just checking for true statements. Okay, if they're true for both, then that is in fact our point of intersection. And again, we'll actually check some answers when we work through our notes tomorrow. Okay. Harper or Jordan or Sophie, could you shut that door, please? Okay. As we graph lines, there are 3 things that can happen. We could have lines that intersect, which is exactly what we just saw. Okay, where lines intersect. In that case, there's one solution. Another name for this type of system is that it is consistent or independent. I don't really care about knowing those names. That's another reason why I don't want to throw math Excel questions, because they might actually ask that. Anyways, we could also have lines that are the exact same. Okay, where we have one line and we just stack another right on top of it. When they're the same, we say that they have infinitely many solutions. And then the last thing is if we have parallel lines, obviously they will not intersect. That is the definition of lines being parallel. And thus there would be no solutions. Okay. A lot of your homework will be graphing lines and just simply telling me where they intersect. But know that another way that we could solve a system is by creating a table of values. Now, a lot of times when we're solving systems, this may not be the most efficient. It helps when we're solving maybe something like more application-based. But let's just real quickly think about how could we come up with a table and just simply find the solutions here. So the first thing, let's call this equation 1. And then equation 2. And so what I'm going to do is I'm going to make a table of x's and y's. This set of y's will be from equation 1. And this set of y's will be from equation 2. And so what we're looking for here, when we plug in x values, which I have no idea where to even start. I'm going to just kind of take a guess of where they might intersect, which again, I have no idea. But then as I plug in x values, that might tell us kind of where we should start plugging in other values to pin down where we get the same points here. So let's start with an easy value in x equaling 0. So for equation 1, that would be 0 minus 2y equals 4. And thus y equals -2. Then for equation 2, I have 3 times 0 plus y equals 5. 3 times 0 is just 0, and I get y equals 5. So right now I can see that the y values, they're not super far apart, right? They are kind of close. One's negative, one's positive, but they're not the same, telling us that we should keep on guessing. Now from here, I'm like, okay, should I try maybe a positive value, maybe a negative value, and see which set of those y values are a little bit closer? So let's just try, let's go to +2 and see what happens. So in the equation, I have 2 minus 2y equals 4. So I'm going to subtract the 2, so negative 2y equals 2, making y negative 1. We'll do the same thing with our equation 2, so 3 times 2 plus y equals 5. So that's 6 plus y equals 5. Subtract 6. And look at that, we get y to be negative 1. That went a lot quicker than I expected it to. That was kind of nice. And look at that. This is exactly what we're looking for, where we can get an x value that when we plug it in, we get the exact same y's in both cases. So we got a little lucky there. Okay, I didn't need to plug in any other x's. We have already pinned down where they intersect. Now, when you're working through this, again, if you plug in 2, just look at the y values. Okay, are they closer or further apart than the first x value you plugged in? That should guide what should happen next. Maybe you continue to plug in positive numbers. Maybe you look at negatives. Okay, but as you plug in each x, you should get an idea, am I getting closer to finding where these lines intersect based on how far apart the y values are. Okay, again, this isn't typically the best way to solve a system, but nonetheless, it is a way that we could solve any system by creating a table of values. Once you're done here, go ahead and flip over the page where we're going to work through an application. This is something that shows up quite a bit with systems, both with what we're going to do, and you're going to get some SAT related stuff related with applications as well. All right. It says the diagrams show the birth lengths and growth rates of 2 species of sharks. If the growth rates stay the same, at what age would a spiny dogfish and a Greenland shark be the same length? Okay, so anytime we have a systems of equation, defining the variables is so important. Okay, so we're thinking about what are our unknowns. So anytime we're defining variables, okay, what are the unknowns? Which another way to think about that is, what are we solving for? So that's always, when you see a word problem, a really good place to start. What are our unknowns, and what are we specifically solving for? And if you just go back to the question, that kind of helps us with that. It says, if the growth rate stays the same, at what age? That's an unknown. The age, right? We don't know any age of these sharks. But that is something that's changing. Would they be the same length? Okay, so we can let x be, and almost always, if we have something that deals with time, that's a good variable for your x. So x is the age, and that would be in years. Okay, the growth rate, we have 0.75 per year. And then 3.75, is the starting length. Yeah, so per year. And that means y is the other unknown, which is the length of the tiger, or length of sharks. Okay, so length, and those are measured in centimeters. So length in centimeters. Okay, and again, anytime you're defining variables, make sure you're specific about them. Okay. Again, I'm going to always encourage you all to start with the defining of your variables before you go ahead and start to build equations. Because now we can build our equations. I'll show how we're going to tie in some function notation stuff. That's another thing we'll continue to do. So I'm going to let f of x be the equation for the Greenland shark and g of x be the equation for the spiny dogfish shark. But at first, we'll just use x and y, just so that, again, we're using the variables we already defined. So starting with the Greenland shark, and I'll do that in red, we know that the length of the Greenland shark, which is y, well, it starts at 37 meters, and then we're adding on how much it grows each year, which is 0.75 centimeters per year. So 0.75x, right? So that length times every year is how much it's growing each year. So the growth rate times the variable x, representing the number of years. And then our spiny dogfish equation will almost be the exact same. We'll have the growth rate of 1.5 times its age plus the start or the birth length at 22 centimeters. All right, now we can start to graph these. And notice that I gave us a graph that is blank because we have some bigger y-intercepts, that it might be helpful for us to change the scale on the graph and then graph each function to ultimately answer this question. Okay, so when we graph these, we want to consider where are we starting, okay, and what is the y-intercept going to be? Or excuse me, what is the slope and how can we make sure we're fitting that slope as we go from one point to the next? So I'm noticing that the y-intercepts are pretty far up, right? 22 is the smallest. One thing we can do, kind of like when we made scatter plots, is make that broken line and just start the graph a little bit further up. So let's start this at 20. Then I'm wondering if I go up by 2s, am I going to get, I don't know how far up I want to get to, but I want to make sure I can find where these intersect. So I want to make sure I probably get up to like 60. So 22, 24, 26, 28, 30. I don't think it's going to work. Let's go by 4s. I think that might be a little bit better here. So 20, 24, because I write big, I'm going to skip the labeling on the 24 and go 28, 32, 36, 40, 44, 48, 52, 54, 56, 56, 60, 64, 68, 72, 76, 80, and 84. And that should be plenty. Let's let our years go by 1s. That should be good. Is this going to work out nice when we go ahead and graph this? Why not? Right. Because our slope is 0.75. And then 1.5. What can we do? Let's just try it. Let's see if we can't maybe estimate and then kind of see if we can't pin down this answer. At least get a rough estimate. All right, so let's start with the Greenland shark at 37. So this was 40, so 37 is just above this. And basically, with our slope of being 0.75, remember that 0.75 is the slope, which is our rise over run. So I'm going to put that over 1. We can still go up by 0.75 and over 1. It's just not going to be by very much. Okay, so 0.75 wouldn't even be up an entire 1, so I'm just going to be barely up. Gosh, dang it. We scaled this graph in a way that we're not going to be able to find where they intersect. So we're going to skip this part. We definitely should have probably gone up by, 2s would have been better. 1s would have been best. Yeah, I think we should have gone up by 1s. Oh well. Okay, anyways, the main thing that I wanted to work on here was building the equations. This is something we'll continue to do with just about every lesson in this unit, is get a system, some sort of word problem, and work on building those equations. Okay, so we'll skip the graph and the lines. The scaling just doesn't work out that great. We need a bigger graph paper. So let's move on to the last thing we have in our notes, which is classifying a system without graphing. Now, again, the language they use here is not language that I need us to know, okay, but the language here is that independent means that there is one solution. The dependent means that there are infinite solutions. And the inconsistent means that there is no solution. Now, when we're checking these without graphing, this goes back to what we know about lines, okay, and slopes, right? Perpendicular slopes intersect. Parallel slopes are the same, and so these are things we all want to think about. Basically, we're going to be comparing slopes here. So when we're looking for no solution, we're looking for parallel lines, which means the slopes are the same.